So to generalize series a little bit, and to move on towards our big goal of the chapter, we have the power series. And this is section 11.8. Specifically, a power series is just like a generalized geometric series, but it's kind of generalized to the point where it's no longer properly a geometric series. So a power series is a series of the form c sub n times x to the n, where x is a variable. And the c sub n's are just a label for the coefficients to this variable. So we have a little bit of a convention just to make things easy for ourselves. If I were to plug in 0 for this series, I would have a very big problem for the first term, because the first term would be 0 to the 0. But instead what we do is we just call that term 1, although specifically we'll have c sub n times 1 plus, not c sub n, we'll have c sub 0 times 1 plus c sub 1 times 0 plus c sub 2 times 0, etc. So to reiterate, even though the first term is indeterminate, technically, if I were to do all the work for the limit kind of in general, I would still end up having the first term is 1. So I can generalize the power series just one little step more. If I have the sum from n equals 0 to infinity of whatever coefficient times x minus a to the power of n, then this is a power series centered at a. The first power series I wrote up above to define it would technically be centered at 0, and this one is basically just a horizontal shift of the one I wrote before. But what we want to know about power series is values of x for which they are well defined. If I choose my x value to be particularly large, then maybe I create a series which diverges after I plug in for x. If I choose my x value small enough or close enough to the center, then maybe my series after I plug in for x will be something which converges. And I might have to do various types of tests in order to verify these things. But what is true for any power series one of three things must happen. One, the series converges for all x values. Two, the series converges at exactly one spot, which is always the center. So the power series will always converge at the center, because at the center you have a power series of pretty much all zeros. For 3, there is a small interval with the center centered at around the center. There's a small interval around the center of the power series for which the power series converges, and outside of that interval it diverges. And we can get this with the basic geometric series. The geometric series will converge on some interval. As long as the common ratio is smaller than 1, it'll converge. But if the common ratio, that r, is bigger than 1, then it's going to diverge. So how we determine that? Well, with power series, it's pretty much always the root or the ratio tests. For example, if I had a basic power series, n equals 0 to infinity, let's have x minus 1 to the n divided by n. Well, this is the same thing is having 1 over n multiplied by x minus 1 to the n. So this is technically a power series. Here's my c sub n, my coefficients, which are dependent on n. And here is my x minus a to the n, with negative 1 is the center. And it'll ask a question like, find all x values for which the series converges. Find all values of x for which the power series converges. Now I stuck one of these on the last test because it's actually a fairly straightforward question to answer. So I have this kind of a series. I have an x in place of having some other number, but I want to test it for convergence and divergence. But since I have an x to the n here, I think I'm going to use the root test on this one. Which means I'm going to need the limit as n goes to infinity of the nth root of x minus 1 to the n over n, and this should be in absolute values. Which looks like limit as n goes to infinity. If I distribute this radical around, I should have absolute value of x minus 1 to the n over n divided by the absolute value of n to the 1 over n. But since my n's are positive, I don't really need to have an absolute value down there. But this x value is determined separately from the n's. It's an independent variable. It doesn't depend on the n's, and the n's don't depend on the x's. So, technically, when considering the n, this x is just some other constant. And I've given this kind of a limit as a fact. What we're going to have here is that this is equal to x minus 1 times 1 over, the limit is n goes to infinity of n to the 1 over n, I have said was equal to 1. And so I have the result of my limit. The problem is it's a variable, it's not a number. But I know that the series must converge if this limit, so I'll give this a L equals, if L is less than 1, which means I converge if the absolute value of x minus 1 is less than 1. So when I have my x minus a here, this is the center of the power series. This number over here, when there's no coefficient on my x's there, this number over here is called the radius of convergence. Which is a special number that we're going to need for the next section. But what it can provide to us is it gives us a little prototype for an interval. So if the absolute value of x minus 1 is less than 1, that means, let's see, either x minus 1 is less than 1, or negative 1 times x minus 1 is less than 1, meaning x minus 1 is greater than negative 1. Which says, let's see, negative 1 is less than x minus 1, which is less than 1. And if I add 1 to all three parts, I have 0 is less than x is less than 2. Which is an interval. This tells me that I'm guaranteed to have convergence for my series as long as x is in the interval 0, 2. But what happens is if x is equal to 0 or if x is equal to 2, we can look right up here. If x is equal to 0, then I have the absolute value of negative 1, which is positive 1. This limit would end up being equal to 1. If x is equal to 2, I get the same story. The limit is equal to 1. Now the root and the ratio tests are both inconclusive when that limit is equal to 1. But if x was less than 0, so if x was a negative number, then I would get divergence from the ratio. I used root test. Or if x was greater than 2, then I would also get divergence from the root test, because the resulting limit would be either greater than 1. Actually, no, the limit would be greater than 1. So, to check these, I would check for convergence of the endpoints by plugging in these values. So for my series, n equals 0 to infinity of x minus 1 to the n over n, I would instead evaluate this. Let's call this a letter, p of x equals. So I want p of 0 equal to n equals 0 to infinity, negative 1 to the n over n. But that's the alternating harmonic series. I know that that diverges because I've done my homework. I said diverges, but I meant to say converges. We could just say we use the alternating series test for that. But p of 2 would be equal to the sum from n equals 0 to infinity of 1 to the n. 2 minus 1, yes. But this is the harmonic series. And we should all know by now that this diverges. So what we can conclude is that the series n equals 0 to infinity of x minus 1 to the n over n converges for all x values in, let's see, it worked for 0 and not for 2. So I go from 0 up to 2 and leave that one open. Not technically any new material, but we have a reason to apply it in this particular fashion. So this interval here is called the interval of convergence. And it's something we're generally interested in knowing. But according to what I said before, the interval of convergence could potentially be all real numbers, or it could just be only the center. And standard examples of those, if I have the sum from n equals 1 to infinity of x to the n over n factorial, here I want to find the interval of convergence. Actually, why don't I just say find the radius of convergence? I don't feel like doing the extra work to test the endpoints. Then, let's see. I would have to do a root or ratio test because all of these power series are going to have x to the n's, which basically say that you should do the root or the ratio test. That's if it's not a really easy series. But I have an n factorial, so I'm going to use the ratio test. Let's see, I'll have the limit as n goes to infinity, absolute value. I'm supposed to use x to the n plus 1 over n plus 1 factorial divided by x to the n divided by n factorial. Now if I simplify my fraction, I should have x to the n plus 1 over n plus 1 factorial times x to the, no, n factorial divided by x to the n. These x to the n's will cancel, leaving with just a single x up there. And this n factorial, this n plus 1 factorial is the same thing as n plus 1 times n factorial, and I can cancel those. This gives me the limit as n goes to infinity of the absolute value of x over n plus 1, which is already positive. So I have the absolute value of x times the limit as n goes to infinity of 1 over n plus 1. But this limit is 0. I have the absolute value of x multiplied by 0. So I get 0. But 0 is always less than 1. So this converges regardless of what x is. And so when this happens, we say that the radius of convergence, ROC, is infinite. This is a series which converges for all x values. On the other hand, if I took this to the opposite extreme, we'll have the sum from n equals 0 to infinity of x plus 4 to the n times n factorial. I'll multiply instead of divide by n factorial. Maybe the opposite will happen. Well, since I have an n factorial again, I'll just use a ratio test. And generally, I think we'll find that the book is going to be using mostly the ratio test for these problems. So if you want, you could just stick to the ratio test all day, every day. So what happens here is I want the limit as n goes to infinity of n plus 1 factorial times x plus 4 to the n plus 1 divided by n factorial times x plus 4 to the n. And I don't have to do any work to simplify my fraction because it's already done. This will cancel with x plus 4 to the n up there, leaving just one x plus 4 on top. And just like I had it before, the n factorial will cancel with most of this factorial, leaving me with just an n plus 1 on the top of the fraction. So this is equal to the limit as n goes to infinity of the absolute value of n plus 1 times x plus 4. Or if I break up this absolute value across multiplication, I'll have an x plus 4 outside of the limit. And I'll have the limit as n goes to infinity of n plus 1. Now this is supposed to be less than 1. But this limit right here, this limit as n goes to infinity of n plus 1 is infinite. Unless x is equal to negative 4. Because if x is equal to negative 4, then this is equal to the limit as n goes to infinity of negative 4 plus 4 times n plus 1, which is equal to the limit as n goes to infinity of 0 times n plus 1, which is actually 0. Now, some of you might be a little upset because 0 times infinity is an indeterminate form. And when we have 0 times infinity indeterminate forms, we're supposed to do a bunch of work to try to maybe flip fractions or something, or try to do L'Hopital's rule. But what the difference is, 0 times infinity is an indeterminate form because you don't actually have 0 and you don't actually have infinity. You have two things, one of which is going towards 0 and the other which is going off towards infinity. And when you multiply those together, you don't really know what happens at the end of forever. However, in this case, when I plug in negative 4 for x, I get actually 0. Not something which is close to 0 in a limit, but I get actually 0. So this is a 0 which is a coefficient of something, giving me actually 0 inside of my limit. So I have the limit as n goes to infinity of 0 instead. But if x is not equal to 4, then I would have some number, a positive number, multiplied by infinity, which is certainly greater than 1. So this series converges only when x is equal to -4, which just so happens to be the center of my power series. A power series will always converge at its center, but what we don't know until we do a test is whether it converges for all real numbers or just some real numbers. So the bulk of 11.8 is simply asking for the intervals of convergence or radius of convergence of various power series. But what we're really interested in is 11.9, which is representations of functions as power series. Now, if I had a very simple power series, where my coefficients were just constant, if I had 17 times x to the n, well, this is basically a geometric series now. So I'll call this one S. And I know that if S converges, then S will be a geometric series. And when a geometric series converges, it's always equal to a particular formula. We'll have S is equal to basically A over 1 minus R, but in this case, A is the first term, which is 17 divided by 1 minus x. So this is a function. So if f of x is equal to 17 over 1 minus x, then f of x is equal to the series n equals 0 to infinity of 17 x to the n, but only when the series converges. Because as a geometric series, I have here S as a geometric series. This will diverge if x is greater than 1, but it will converge if x is less than 1. I guess I should say an absolute value. S has an interval of convergence which matches the geometric series of -1 to +1. I can't be equal to -1 or +1 because then I'll either be adding an alternating series of 1s and -1s, or I'll be adding an infinite number of 1s, and that's bad. Which means that 17 over 1 minus x is equal to the sum from n equals 0 to infinity of 17x to the n for all x in the interval -1 to 1. But otherwise, the series will diverge and it will not be equal to the function. And the great big goal of this chapter is to represent any function as a power series. And the reason we want that is because a power series is an infinite series which converges to something. But if I cut it off at a partial sum, then that partial sum is going to be an approximation of some number. But if my power series is equal to a function, then my partial sum will actually be an approximation of some function. And the value in this is that a polynomial, which is kind of like a finite power series, is significantly easier to deal with and calculate with than some of the arbitrary functions we have. So for example, if you were using a calculator, the calculator is not using the sine function to evaluate sine of x or sine of 15 or whatever. It's actually using a power series, or actually a power series representation up to so many terms of sine of x, because it's much easier to calculate. So let's take some other types of power series, or not power series, but some of the functions we can represent depend on this a over 1 minus r. So if I had, for example, x squared over x plus 1, and I want to represent this as a power series, I first have to try to force it to fit the formula a over 1 minus r. But I don't quite have that because I have addition on the bottom, and I could probably keep the x squared on the top. That's just fine. So I'll rewrite it so I have a 1 minus. So this is x squared divided by a 1 minus, and that should be a negative x. Because if I simplify this, I'll have my 1 plus x again. So since this fits a over 1 minus r, that means this is equal to x squared times the sum from n equals 0 to infinity of negative x to the n. Or I could rewrite it, x squared n equals 0 to infinity. I'll have a negative 1 to the n times x to the n. Or not x squared here, but I can multiply the x squared into the series. I'll get negative 1 to the n times x to the n plus 2. So I've represented my function as a power series. If I was so inclined, I could also rewrite this as negative 1 to the n times x to the n. Nope, not n equals 0, from n equals 2. Because over here on the left, if n is equal to 0, that means my first term has an x squared. And I'll have a negative 1 squared, which is positive. Versus here on the right, I started my series at n equals 2, I went up to infinity, and so my first term is an x squared with a negative 1 squared, which is again positive. Adding and subtracting 2 doesn't change whether or not this exponent is even. So this is technically the same power series, we just wrote it a little bit different. But whenever I find a power series representation, I should be aware of what the interval of convergence is, because this function will only be equal to the power series on its interval of convergence. So I'll go ahead and kind of skip it a bit. If we do the ratio test, actually if you do either, we will find that the radius of convergence is 1. It actually doesn't matter that this x is squared or not, or that I have x to the n plus 2 or anything like that. And in particular, the interval of convergence will not include the endpoints. Let's see, the center for this series is at 0, so this is negative 1 to 1. So this function that I wrote is equal to this power series on the interval from negative 1 to 1. So we'll do another one, because I don't think the book does this as an example. What happens if I have 2x over 4x plus 2? There's actually a couple of different things I could do with this to find a power series representation. In fact, just so that this doesn't simplify, I'm going to change this 2 to a 3. And there's two ways to go about this, technically. One of them is better than the other. I could take my 2x divided by 4x, and I could have plus 4 minus 1. That simplifies to 2x over 4x plus 3, but this is also equal to negative 1 over 1 minus 4x plus 4. Not negative 1, but negative 2x. And I can build a power series out of that, which looks like negative 2x times the series and equals 0 to infinity of 4x plus 4 to the n. Now this one has a center of negative 1, but it has a radius of only 1/4. I should add here, verify with root or ratio. On the other hand, so we'll call that version A. Version B is, let's see, I'm going to divide out that 3. So this is 2x over, I'm going to factor out a 3. So this is 3 times 4 over 3x plus 1. And the reason I do this is it actually gives me a much better interval of convergence. Okay, so this is equal to, we'll write it as 2x over 3 on the top of a fraction divided by 4x over 3 plus 1, or I should have 2x over 3 divided by, let's see, what I did for the first one was I did 1 minus a negative. So if I were to write that as a power series, I would have a 2x over 3 out here. I'd have a sum from n equals 0 to infinity, and I would have I'd have negative 4x over 3, that's my r, and that would be raised to the n. Now this one has a center of 0, versus that other one had a center of negative 1. And this one is going to have an interval of convergence, not interval, it's going to have a radius of convergence of, let's see, 3 over 4. Which is technically 3 times as big as the radius I had over there. And I could have technically done this a third way to change the center of my series yet again. So if I had 2x over 4x plus 3, I could have written this as 2x over 4x plus 2 plus 1, which is equal to 2x over 1 minus negative 4x minus 2. And that would have given me yet a third series of negative 4x minus 2 to the n. Now this one requires some rewriting. I can't tell for sure what the things are going to be based on my experience, but I can factor out a 2, and I can factor out, actually I'm going to factor out a 4 and a negative 1. So I'll have a negative 1 to the n, that takes care of the negativity. And if I factor out a 4, I'll have a 4 to the n, and what will be left inside is x plus 1/2. So this will have a radius of 1/4 and a center of -1/2. So here I have 3 totally different power series. Each one has a different center, and 2 of them have a radius of 1/4, and the other one has a radius of 3/4. So this one is the best, and this is actually the technique we're going to want to be using most of the time. And that is, I took my constant term and factored it out so that I had a +1 or -1 at the end. These others, they'll technically work, but they're not so great. So, the reason I bring this up is technically there are infinitely many power series representations for any function. So don't be totally surprised if you do some work and end up with a slightly different power series than somebody else. They might still both be right. It's just maybe one will have a larger radius of convergence than the other. So another way to find some power series representations of maybe some other functions is with differentiation and integration. But this requires a fact, which is actually not too difficult to prove relative to some other things. By the end of this chapter, we're going to have a specific method of creating power series, which is going to work for any function out there, and it's pretty much one of the best ways. And a lot of times, it lines up with some of the methods we've been using to find power series representations so far, as well as this next one. So the bonus is we can differentiate and integrate power series, because a power series is technically just a sum of things, and differentiation and integration will both distribute across sums of things. It requires a little bit of extra work to make sure that, oh hey, if I take the derivative term by term of the power series, then it's going to converge to a function which is the derivative of the original series. But we can go ahead and take these as established facts because they've been proven by somebody. Because even though every function has multiple power series representations, each power series can only represent a single function. So, if you have a power series, the sum of n as n equals 0 to infinity of c sub n times x minus a to the n, so just a generic power series. If it has a radius of convergence, r, which is positive, so it converges somewhere other than its center, then the function defined by the power series, or the function which has this power series representation, is differentiable, and therefore also integrable, on the open interval of convergence. So maybe not at the endpoints, because the derivative or the integral might gain or lose one of the endpoints in the interval of convergence, but it's always works within the radius of convergence. then the derivative of the function, or the derivative of the power series, will be equal to the derivative of each of the terms. So the c sub n is constant, it remains unchanged, and I just use the power rule on the x minus a to the n term, so I'll have n times x minus a to the n minus 1. We'll notice in the derivative we started the series at n equal to 1 because the n equals 0 term is going to be constant in the original series. So when I take its derivative, it goes to 0. So we'll just chop it off of my sum notation. And 2, if I want the integral of f of x with respect to x, then it's going to be the new power series plus the big constant of integration. Particularly, I'm going to take the integral of each of the terms, so I'll sum from n equals 0 to infinity, c sub n times x minus a to the n plus 1, all divided by n plus 1. So it's just the power rule again. And the great benefit here is that the radius of convergence is unchanged by differentiation or integration. The reason I care about this is it increases just a little bit the number of power series that I'm able to, or the number of functions that I'm able to easily represent as a power series. So without performing all of the steps, which are covered in other places in the video, I'm going to do some sketches, basically. So I want to find a power series representation of the natural log of x plus 1. Now this is not a fraction. I can't find a power series representation because, it's not a fraction. I can't use the geometric formula to try to build the series. But what I can do is I can take its derivative. The derivative of the natural log is basically 1 over. This will be 1 over x plus 1 multiplied by 1 from chain rule. But this has an easy power series representation. N equals 0 to infinity. Let's see. This should look like negative x to the n, which is equal to the sum from n equals 0 to infinity of negative 1 to the n times x to the n. But natural log is equal to the integral of the derivative of natural log. This is the fundamental theorem of calculus thing. The integral will undo the derivative, or the derivative will undo the integral. But if I'm taking the integral of a derivative, then I have a mysterious plus c hanging out there. So this should be the integral of 1 over x plus 1. But I have a power series for 1 over x plus 1 right here. So this should be equal to c plus the sum from n equals 0 to infinity of the antiderivatives of each of the terms. So the negative 1 to the n is unchanged because I'm taking an antiderivative with respect to x. So I'll have x to the n plus 1 divided by n plus 1 down here. But since the integral of 1 over x plus 1 is the natural log of x plus 1, then that means that we have a power series representation for the natural log of x plus 1, which is this c plus n equals 0 to infinity, negative 1 to the n, x to the n plus 1 divided by n plus 1. Now I can tweak my representation a little bit here, because in this power series, if n is equal to 0, I'm starting with the linear, or x to the 1 term. So I could rewrite this as c plus sum from n equals 0 to infinity. Actually, I'm going to start from n equals 1. So I'll have negative 1 to the n minus 1 times x to the n divided by n. That's what I get if I change my index by just a little bit. Now to solve for the c, all I gotta do really is plug in a number to both sides and make sure that they line up. If I plug 0 in, I'm going to have the natural log of 0 plus 1, which is equal to the natural log of 1, which is equal to 0. And I'll have c plus the sum from n equals 1 to infinity of negative 1 to the n minus 1 times 0 to the n over n, which is just 0 everywhere. Which means for this time, my c is equal to 0. But I found a power series for natural log. What I should be interested in is whether this power series is actually equal to the natural log somewhere interesting. However, this series right here has a radius of convergence of 1. Which means, after I did this integral stuff, that this series here, natural log of x plus 1 equal to the sum from n equals 1 to infinity, negative 1 to the n minus 1 times x to the n over n, has a radius of convergence of 1 also. And I can do similar things to find the power series for arctangent, or if I needed to find the power series of an arbitrary integral of something, I could find the power series of the thing inside the integral and then integrate the power series later, which is especially handy if the integral is impossible or kind of gross. For example, the integral of 1 over 1 plus x cubed dx. I don't really know how to handle that, which is a lie. I do know how to handle this because I could use partial fraction decomposition. Or I could find a power series for the thing inside the integral. It's equal to 1 over 1 minus negative x cubed. So this is equal to a power series when the power series converges. This is equal to the integral of the sum from n equals 0 to infinity of negative x cubed to the n. If I do the root test, I'm going to get the radius of convergence, ROC, is equal to 1. But I can do this integral anyway. This is going to be the sum from n equals 0 to infinity. The integral basically moves in, and all I have to do for this guy is the power series. So why don't I rewrite it so it's a little more obvious first. For the integral, this negative x cubed to the n looks like negative 1 to the n times x to the 3n dx. And when I integrate that, I'm going to have, let's see, negative 1 to the n times x to the 3n plus 1 divided by 3n plus 1. And I should have a plus c hanging out here. I would technically kind of have a plus c for every term, but we wave our hands a little bit on that one. The problem is, after I find a power series for a function, it's kind of difficult to determine what that function actually was in the first place. But this would at least help us evaluate an integral as long as it's on the interval of convergence. So what we're going to be doing next time is we're going to be crafting special types of power series, or rather it's a specific technique of building a power series which will work for any function out there. And they'll always have a radius of convergence which is positive, which is a very nice thing.